Now, I know all these equations and how they came about and how they fit together, but I don't know anything about optimization. So that's your part. Yes?
So if your free length is more than 4 times your diameter, then it buckles?
Yes. Yeah, that's a limit. You don't want it to buckle. So you want to keep the free length less than 4 times that. So I guess while you brought that up, there are a bunch of equations that depend on each other and interact in your optimization procedure, but there are other equations like this that just set limits. Like this is a limit setter. This one here is a limit setter. They're just setting limits. They're not really doing it. I don't know if you can say anything more about how you optimize with all these equations.
We will talk about it later.
Okay.
In the context of calculus. So.
Yeah.
I have one more question. So is failure, is that like defined as buckling, or like is deflection a failure as well? Like what, what is deflection?
Yeah, failure, usually failure comes about when you compress it and get a force of compression here that the shear stress that you impose by compressing it is greater than the yield stress. So that's a failure.
Okay.
And rather than design to that, a lot of springs design so that when you get the shut length here, maybe I didn't say it very well, is when you compress it all the way down to where all the coils touch each other. Most of these springs I can't compress to the shut length. I don't know if any of you are bodybuilders and can take that big job and compress it, but I can't. But here I got this little one compressed. That's shut length. And you want to have it shut and still not yield. Obviously, when I shut it, that's the most force I can put on it. And at that force, I don't want it to be yielded. I want it to be less than this. But the criterion we have is a safety factor too. So I want to be less than half of the yield stress when I shut it. Now, as I said, I've given this in my 466 class. This problem was, I think, about 4 years ago. So I took it from archives. But we did do a design, and interesting, some of the students in that class have no concept of size and what's reasonable. Sometimes they design things like a spring that's bigger than Neyland Stadium. So don't design a spring that's bigger than Neyland Stadium. It probably isn't necessary to design something that size. It has to make sense. A lot of times, I think, coming from high school, you learn to do equations and this and that, but don't stop and think, does this make any sense or not? So what we try to do when you get on into the design things is also stop and think, does this design make any sense physically? Those are all the equations and things. More to say or questions? Yeah.
When you say that you're designing for the optimal of those values, does that mean that we're looking for the minimum values, kind of?
That's not my area. What do you think?
Well, it's whatever you want.
Yeah.
So you are the master. You ask us what you want.
I suppose it would.
What are the parameters you want to the output?
I suppose it would be cheapest in terms of material. If those
Yeah,
values were all
minimum.
minimum.
Yeah, that sounds like a good point. Minimum. I guess you could have many optimal designs, couldn't you?
Or the maximum force that a certain length spring could
Yeah.
hold or something.
Because you mentioned some ideas about the cost.
Yeah, cost.
So can you suggest some parameters to optimize?
So the minimum of these that works and fits these, I think, would do it. Would be good. Other questions? Yeah.
What exactly is deflection?
Deflection is how far the ends move toward each other when I put a force on it.
Okay.
So here, what is this? 5 inches, say. So I'm going to deflect it. It deflected 1 inch. Sorry for going into engineering units. We use those a lot, but it's how far it goes down. And again, the most it can deflect is till it's shut.
Yeah. The shut line.
Once it's shut, it can't deflect anymore because everything's on top of each other. Other questions, comments about design? Any of you mechanical engineers in this class? So how long do you have to go yet?
I'm a freshman.
Oh, you're a freshman, so it'll be a while till you get into this, maybe 3 years. I've been teaching it for a while, but I don't know how much longer, so maybe I see you, maybe not. Any of the rest of you engineers? No? Yeah, what is civil?
Civil question mark.
Okay. That's a good thing to not be sure and see what you like. Okay, other questions?
I have a question. Well, from my high school, the only connection I have between springs and mathematics is the Hooke's law.
Yeah,
And that's what you never mentioned yet.
well,
So is it hidden somewhere? Or?
this is the part of the Hooke's law. G. G is the shear modulus. The Hooke's law part of this is that gamma is shear stress over G. Gamma's shear strain, and tau is shear stress. And the reason I didn't go into the stress strain things more is because none of you have had any mechanics courses, and you won't for a while. So you don't know about those things. The one that you're perhaps familiar with is the elastic modulus. Strain is sigma over E. This is the classical Hooke's law, but G is also part of the Hooke's law. So good question.